And yeah, good morning, everyone. Welcome back to the Toronto Area Seminar. Today we are glad to have Silviu to present his work on generalizing auto-distribution using counterfactual data augmentation. Silviu Pitis is a fifth-year PhD student at U of T here, working with Jimmy Ba. His ultimate research interest lies in the normative design of general-purpose artificial agency, like how should we design AIs that solve general tasks and contribute positively to the society. His current work focuses primarily on goal design of RLD agents and designing sample-efficient reasoning agents that can achieve a wide range of different goals. He holds a master's degree in CS from Georgia Tech and a JD from Harvard Law School and a BBA from Schulich School of Business. Cool. Looking forward to your talk, and the stage is yours.
Awesome. Well, thanks for having me. Happy to be here. Yeah, so I'm talking about counterfactual data augmentation and the view to generalizing out of distribution or enabling out of distribution generalization. And the bulk of this is going to be two papers that I did with Animesh here at U of T. So these are joint work by myself, Elliot Krieger, Ajay Mandalkar, and Animesh. Now, Elliot did a talk on these Thursday last week. So if any of you were at that seminar, I apologize. There's going to be a lot of overlap. At the end of the talk, if I have time, I'll touch on a more recent work that uses a lot of the same principles to basically do data augmentation to generate out of distribution data and use that to enable generalization. Okay, so let's talk about data augmentation and reinforcement learning generally. So we'll look at some past data augmentation methods like hindsight experience replay and Dr. Q. And we'll talk about global independence property that enables them to work really well and improve sample efficiency. And then more generally, we'll talk about factored MDPs briefly, which are a very sort of older topic that people have shown to that can improve sample efficiency exponentially when there's global factorization. The key innovation of our work here with the counterfactual data augmentation is actually to recognize the existence of local independence, which makes this a much more flexible framework. So we can apply it in a lot more places. And the places that we're going to be particularly interested in are factored settings where a state can be divided into multiple factors or slots. And cases where we have some sort of causal reasoning over those. I'll talk about our two algorithms. We'll talk about some challenges and future work with the algorithms. And then if there's time, more generally with the superb work that I've done more recently. Scope of this. Oh, and please interrupt me if there's anywhere clarification or questions. Scope of this is going to be off policy RL. And why off policy? Well, we're going to assume that there's some offline buffer of data that's generated by some empirical policy. And so if we think of our state action space as this, our empirical policy might cover something like this. And what we're interested in is learning a new policy. It's going to be different from the empirical policy, maybe because we're trying to generalize to a new task, or empirical policies are historical exploratory policy, and we're trying to explore the environment to learn the current task. But in general, our empirical policy, it generates this data, but we're going to want to learn a new policy that's going to maybe act on some larger data set, or just maybe they don't overlap, or they don't have perfect coverage of the old data set, but it's just different. So it's going to be a non-overlapping data set, and there's a bunch of out of distribution stuff here with respect to the original data set. Now, normally in online RL, we have this little arrow here. So the agent sort of updates their policy, they roll out the policy in the environment, they collect more data, and they start to get some of this out of distribution data, and then they can learn it. But we've seen a lot of rise of offline RL methods lately where the offline buffer is fixed. So the agent never actually gets to explore. So we can't see this data by any other way than augmenting the original data. And so the question is, can we take data here and somehow make valid data out here that our agent can train on? That's what we're going to try to do. Here's like the very brief intuition of how we might do this. We're going to assume that the state is factored into objects or slots, like background, foreground, or even state and action are sometimes considered different slots. And we're going to consider that very often these objects are going to be locally independent. It's not going to be all the time, but in this pool example here, there's a blue ball and an orange ball, and they're physically separated. And so their dynamics are not affecting each other. When they are locally independent, then we propose to basically exploit that independence and swap the data to form new samples. And these samples might be out of distribution. So we take the blue ball from the first transition we observe here, and we take the orange ball from the second one, and we just mash them together to form this new sample that wasn't in our buffer originally. And doing this, we show that it can accelerate the speed of off-policy RL. This is online pretty quickly. And also in an offline task, we can generalize to an entirely new task that just didn't appear in our buffer at all. Okay, so this work was motivated actually by some existing methods in RL and also how I personally reason about the way objects interact in the world. We've seen some really large sample efficiency gains in hindsight experience replay, which is something that I worked a lot with before. Basically, this is a multi-goal RL. Usually the agent can't learn anything because it basically has no success experiences in its buffer. But if we just imagine that the goal is somewhere else, in particular, we imagine that wherever we end up with, that was the original goal that we were trying to achieve. It's kind of hindsight relabeling of our experience. We're imagining this new data, so we're augmenting it, and we're able to solve these tasks that were not solvable before. In the visual data augmentation sense as well, we get like 10 times sample efficiency improvements by doing these pretty standard data augmentation that we've seen in, say, for example, ImageNet. So taking these two things, how can we put them under the same framework? And the idea is that they both exploit this global independence property of these causal mechanisms behind the transition dynamics. So in the hindsight experience replay, we notice that the goals that the agent are pursuing, well, the goal at the original time step and the next time step, it's the same. And the dynamics of that goal are completely independent of the actual state action transition dynamics once we condition on the action. So yes, the goal can influence the action, but once we condition on the action, the next state is now independent of the next goal. Similarly, in the visual data augmentation sense, it is our visual characteristics of the scene. So like you can consider the camera angle or the crop, that's also independent of the underlying physical dynamics. And so we can change that without affecting what's happening in the underlying scene. And you can think of both of these as examples of a more generic framework where whenever we have these two independent components in the transition dynamics, we can swap one of them out and then switch it out for something else. And that's just the data augmentation take on a more classic framework for MDPs called factored Markov decision processes. This is an example from a early 2000s paper where they have these 4 computers and basically, if one of the computers fails, it can affect the next computer in the chain and cause it to fail, and so on. But there's only the two adjacent computers interact at any given time. And so the process is completely factored because, say, the fourth computer never never affects the second computer directly. Now, the problem here is that, generally speaking, in a very complex process, causal independence is rare. Like, even if you, I guess this isn't the best one. If you were to roll this out, right, M4 still affects M2. And so if we look at the structural causal model for the global transition dynamics, it would actually be fully connected here. And to get an intuition of why this is a problem, we can go back to our pool example, where for the most part, the balls are physically separated. They behave independently. And so we can do this kind of data augmentation that we did before. We take the orange ball, we take the blue ball, we make this new transition. But if we try to do it in the other direction, we get this nonsense on the right, on the bottom right here. And that just tells us that a naive approach to data augmentation, where we just swap out components freely. And that's kind of what we do in hindsight experience replay and also in the visual data augmentation, because they have a global independence property. It's not going to work in general. And that's kind of the main problem that our first paper, Counterfactual Data Augmentation, tackled. And the key insight there was to think about things locally instead of globally. And this is a very natural thing for humans. So long as the two pool balls are physically separated, we can kind of manipulate them in our mind, move them around freely, imagine new scenes. It's only when they collide that we have to pause and wait a second, our manipulation is not right. And formally, we looked at this from a causal modeling perspective. So we took the transition dynamics, we imposed a structural causal model. I don't want to get into the details of causality, but essentially it's just, there's some variables, there's some unobserved variables, and then there's these forward dynamics functions that cause the next state components. And usually when we're doing causal modeling, we think there is one global causal model. And if we were to try to model the global dynamics function using a single causal model, we get a fully connected model here because across all states and actions, the two balls can collide. But if we condition on a subset of the state action space, so this is a local subset, and that's our key idea, say the balls are physically separated, we get rid of those two edges that were causing problems. We get these two independent components, and we can now apply our the same reasoning we did in hindsight experience replay to this problem. So this lets us handle these nonsense samples on the bottom right, basically by rejecting them. So we see in the top row and in the bottom left, we're inside this subspace L where the balls are independent. So we're okay with all of these samples. In the bottom right, we're no longer in the subspace. So the causal model is wrong. And that tells us that our aggregation, so the concatenation of the blue ball and the orange ball in this subspace is an invalid manipulation. And so we reject the sample. And that was essentially the first coda, and we'll get into it in slightly more detail a bit later on. But taking a step back, looking at this more generally, just to see what's going on with this two-armed robot here. It's another example of how we're adding in the actions now. And so the full state action space is this thing. We're dividing it into two local subsets, one where the robot's arms are apart and one where the robot's arms are together. Maybe it's manipulating a single object, but basically if it tries to move its right arm, it's going to move its left arm. In the case where the arms are together, the graph is fully connected. In the case where they're apart, they're separated. And we can actually learn a different forward dynamics model for each of the two neighborhoods. And that's kind of the idea behind the model-based counterfactual data augmentation. So in the pool example, we were just swapping subspaces from our replay buffer. It was kind of a model-free augmentation. Here in the model-based case, we're thinking about actually modeling this causal mechanism for the right arm using one dynamics model and this causal mechanism for the left arm using another dynamics model.
May I ask a question now, or do you prefer?
Yeah.
So for the model-based case, do you guys also do assume that the model is available to you, or do you have to do some sort of causal identification or causal discovery, to be precise?
So I guess it depends on the experiment that we did. In general, to do the causal reasoning, you do need a causal model. That model can be learned, and I'll talk about that in a sec. We did do some causal model learning, but that's one of the challenges with this method. It's not an easy task to do the actual causal model learning. What's more about it is that because we're trying to generalize out of distribution, we are hoping that whatever causal model we learn in distribution is going to generalize out of distribution. So there's like a hypothesis there that somehow whatever causal model we learn is going to generalize better than just the dynamics model that we learned. If we learned a fully connected dynamics model, we think the causal model itself will generalize better than the dynamics model. Question for future work if that happens. But so this is like the key sample complexity result from our model-based paper. It's not super deep, but it shows that we can get sort of the same benefits that factored MDPs offer by doing the local causal modeling. So when we split the dynamics into k causal mechanisms, we're learning essentially k smaller dynamics model for each subspace, for each local subspace. And so that reduces the complexity of learning each of those dynamics model by basically an exponential amount. And the trade-off is just that we have to learn a few more of them because there are multiple local subspaces. And so we need to learn it for each one of those subspaces.
Sorry, sorry to interrupt. Yeah. Can I ask, how do you learn these subspaces? Do you learn them, do you specify them manually? Because yes, the transitions among them are going to be super, right?
Yeah, okay. So you guys just captured the two key parts that we need for this to work. So the two assumptions for counterfactual data augmentation, the actual algorithm, are that the state is subdivided into objects already for us. So it has a factor-based representation. And that just goes back to here, 1, 2, this is a state with 4 factors. And the second one is that we know this causal model. So we know the edges of the graph. Both of those can, in theory, be learned. So for example, the slots could be learned using, say, Z's slot former. And maybe those are good slots to do causal modeling with. Maybe if we had those slots, we can now apply, say, a transformer-based dynamics model, and we can look at the attention map, and maybe the attention inside the transformer gives us the edges of that causal graph. And once we have those two components, then we can apply CODA.
Got it, thank you.
Okay, so on to this topic. Where do these local models actually come from? The first place is just domain knowledge. In the pool example, we knew that if the balls are physically separated, then they're independent. This actually can be learned too if we have this domain knowledge of physical separation. So we could just learn a physical separation classifier. In several of our experiments, though, we just use like a heuristic to say that if two objects are further than 5 centimeters apart, then we're going to treat them as independent. Alternatively, you can learn it, and we did this a bit in our first paper. So here's an example with the pool balls, where they each just have 4 features, an x position, y position, and then a velocity for each. And the idea is we're trying to learn that adjacency graph between the balls at time t and the balls at time t+1. And when they are independent like this, our adjacency graph is going to look like this block diagonal matrix here. And this is just saying that there is a causal relation between the orange ball and the orange ball, but not between the orange ball and the blue ball at time t+1. And one way to think about this is essentially it's telling us the input-output Jacobian of the, if our transition dynamics are continuous and differentiable, it's telling us the input-output Jacobian where it is non-zero. And so that tells us like one way that we could try to learn this just by using a feed-forward neural network is by bounding the Jacobian of the network. And so we know that, say, the absolute network Jacobian is upper bounded by the network mask, and that's been used in like a couple prior works, like the masked autoencoder is, I think, where it was originally proposed. And then it's also been used in causal model learning for a global causal model. The problem here is that a standard neural network, the weights are global. And so if we tried to do this, we would get a single adjacency matrix for the full network. And so what we have to do is take some sort of conditional mechanism, like a hyper network or an attention mechanism that is conditioned on the state in action. And that'll make the weights conditional, and that will give us a different network mask for each state in action. And then we just make this assumption. It's not necessary, like we could learn a latent variable model to get around this assumption, but we make this assumption that if two different state action pairs have the same network mask, then they are part of the same local subspace. So this basically, if we get this network mask for these two pool balls, we say that this is the physically separated subspace. What we did in our original paper, we used this multi-layer set transformer, and we computed M as the product of the attention masks. And surprisingly, this worked without any regularization. So usually what you'd have to do is sort of regularize these weights downward, say with L2 regularization to get the weights small in order to bound the Jacobian values to some very small values when they're 0. But with attention, like the softmax is self-normalizing, and it turns out to work reasonably well on simple environments. So in a sprite world, this worked really well. In a more complex fetch is very sensitive to hyperparameters though. And this just might have to do with the difficulties of training transformers. I admit I'm not like very good with it. Maybe if we tried a lot harder, we could find some way to train these really well, but that's for future work. Okay, so let's assume that we have that local model. We could have learned it, or we could use our little physical separation heuristic. How can we actually use it? Our first paper explained was a model-free usage of the model. So we would sample 2 transitions from the replay buffer. This is T1, T2. We'd take one of the observed samples from the first causal mechanism from the first transition. We take the observed sample of the second causal mechanism from the second transition, and we'd put them together to form this new augmented thing that wasn't in our data set. We had this cute little remark that we can generate an exponential number of samples, and that's just sort of echoing the sample complexity result we saw earlier. In MoCoda, we did this model-based. So essentially what that means is we would first pick a configuration of the parent variables. So we would first pick these three. And I'll talk about how to pick them in a second, but we called the distribution that we sample them from the parent distribution. And once we pick them, then we just roll out this locally factored dynamics model that we learned. So in the simplest case, that's a different dynamics model for every causal mechanism. And we see that here in a different form, and we can see here why the MoCoda approach is slightly more flexible. When we use the original approach and we applied the local causal model, and we found that it was fully connected, we couldn't actually do anything with these samples. We just had to keep the ones in the data set. On the other hand, if in our new paper with the model-based approach, if we found that the graph was fully connected, we could still augment it by applying the model. And this is very similar to Dyna when the graphs are fully connected, but it is also slightly different because if we had a third pool ball, then we could still do something, regenerate that part. Separately, you'll notice that if we were to actually learn a different forward dynamics model for each of these, it's slightly different from computing them all within the same neural network. So there is a subtle difference, but that's just going to depend on the actual architecture that you use for the local dynamics model. The more important part is that we have a lot more flexibility with controlling the configuration of the original variables. So in the original Coda, we just swapped whatever was in our buffer uniformly, and we just accepted the result of that. And that, this is just a general thing that I find unsatisfactory about off-policy RL, is we kind of just accept what's in the buffer usually most of the time, and there is no, I still haven't found a satisfactory argument for what the best distribution to train on is, because it's not the distribution, it's not the distribution that the policy that you're trying to learn would generate is either. It's not a uniform distribution because that gives you a lot of irrelevant samples. It's something that is like some sort of a dilution of the experience that would be generated by your target policy. Also sort of in range of where your current policy is. But if you know of a good answer to that question, I'd be interested in reading about it, but I don't think anyone's ever come up with a great one. But you could see some things that we propose shortly. But essentially, that's the question that we're trying to answer here. We have this parent distribution, and we can control it. So that means that we can kind of prioritize it to target areas of the state space that we're interested in and that we think that our agent should train on. And we model that entirely separate from the causal mechanisms. So this kind of relates to the two questions, the two assumptions that we're making. What's at the original state, so the decomposition of the state into multiple factors, and then what's in the transition, the actual causal mechanisms themselves. So this slide just summarizes the generative process of MoCoda. We first fit this parent distribution to our data set of states. We also fit the factored dynamics models. And then in the augmentation phase, we're going to sample parents. And then once we sample the parents, we're going to apply the causal mechanisms. So it's basically a two-stage approach here. Because we can control, and this is what I was getting at before with the controlling the parent distribution, here is this is kind of like the big empirical result of our MoCoda paper. In our empirical data, this is what our empirical data looks like. We have a fixed data set of an agent that is sweeping a single block to one side of the table. So the big spheres, the transparent spheres are just its goals, and this is an expert agent that is moving the blocks into those two goals. And you can see that the two blocks are never together on one side of the table. But what we want to do in this task is to be able to sweep both blocks to one side of the table. So this is the target behavior here. And like these final states, they just never appear in the buffer. And so we really do need, especially because we're doing this completely offline, and offline RL methods tend to constrain the agent to optimize within the empirical distribution. But we really need to be able to expand our data coverage in order to get anywhere near to solving this task. And with MoCoda, because we can control the state action distribution that we begin our generative process from, we have some control over that. And you can see it down here. This is the same task that we just saw. And the blue dots, the blue region, we plot a dot whenever the two blocks are beside each other. So in the empirical data, the two blocks are only beside each other near the center of the table, because once they're on one side of the table, they're now separated. If we were to do the plane approach, and I'll describe that in a second, we're able to get coverage of the two sides. And this is roughly what the original CODA approach did. So this has no prioritization over the parent distribution. On the other hand, because we're able to control the parent distribution in our approach, we can actually bias it to having more samples within the two goal regions. And that's brings it a lot closer to, say, hindsight experience replay, where basically the contribution of her was the prioritization itself, not so much the goal relabeling. People already knew how to do goal relabeling, but it's this prioritization towards successful experiences or experiences with rewards that are closer to the target policy that really allows it to work well. What's interesting about MoCoda is that the theory, and we're going to get to this on the next slide, kind of tells us how we're allowed to prioritize the parent distribution. And the idea is that so long as the parents of every causal mechanism are in distribution, we think that we're going to be able to generalize well in those regions. So each of the causal mechanisms, the generative causal mechanisms, are going to generalize well on that local part. And so if we combine those two local parts in a novel way, we're thinking the whole is also going to generalize well. And so here's a nice graphic showing this in 2D with just an X and a Y component. This is just the 2D data of our empirical. The empirical data here is just generated by a mixture of Gaussians. And if we assume that X and Y are independent, then we can look at the marginal of Px and the marginal of Py, and then we can just take their product and we get this sort of maximum entropy mixture of marginals here. So this is the highest entropy distribution that matches the marginals of both X and Y. And we think that we're going to generalize well here. And the idea is that even in this region up here where we had no data, X is in distribution and Y is in distribution, and we're asserting that they're independent. And so these new samples are effectively going to be in distribution, even though they're out of distribution with respect to the whole. At the same time, we know not to generate any parents here because that's not in distribution with respect to the parts. And neither would be, say, up here, because that's only in distribution with respect to y, but not with respect to x. Okay, so that was the principles behind CODA and MoCODA. Let's just look at the results quickly. This was from the original CODA paper. It's a pretty simple Pong environment. The state is factored into 3 parts, the 2 paddles and a ball. This is completely offline batch RL. And we can see that if we apply 1 real data to 3 CODA samples, then we get this pretty large boost in performance over the using just real data, or even just using a dyna-based approach. And it effectively doubles our data set size. So with only 50,000 data points, we get the same performance as 100,000, and with 100,000, we get the same performance as 250,000 real samples. This is a more complicated environment here with the, this is a fetch push and a fetch slide. Everyone's probably familiar with the fetch push. There's just a gripper and an object, and we're trying to push the object to the red goal spot. If we apply our unprioritized original CODA here, we get a sample complexity improvement of basically 2x. And this is on top of hindsight experience replay. So the base agent here is hindsight experience replay. If you didn't have hindsight experience replay, you just wouldn't get any success whatsoever. In this more complex environment, we need a lot more samples. So it takes over 10 million samples for the baseline agent to kind of start getting good success here. On the other hand, if we apply CODA, again, we get a 2x improvement in sample complexity, and we also just get higher performance at the 10 million time step mark. And in MoCODA, we already saw that how the agent was able to take an offline data set of the 1 block trajectories and then learn how to move 2 blocks. This is fairly impressive because this kind of data, it just doesn't appear in the offline data set. And yet we still need to apply an offline RL algorithm. So we're combining MoCODA with BCQ or TD3BC here. So these still constrain our agent to the augmented data set. But because we're asserting that the agent is going to generalize well in this augmented data set, because it's actually in distribution with respect to each subcomponent, we see that our offline RL algorithms are basically able to solve this task. Of course, without data augmentation, they have no hope here because it's out of distribution. So that was CODA and MoCODA. We already touched on, I guess, 2 of the most important sort of future work angles here, which is we need to have a better way to infer the local causal model. And we also need to have a way to find what are the slots. So what is the decomposition of the state action space that is going to work well for this? And then the last one, we did do the prioritization. So our little prioritization scheme here, trying to remember exactly how we upweighted this. What we did is we found the state action, the object marginals. So the object XY for object 1 and the object XY for object 2. And we took a uniform distribution over that. And we kind of shifted this distribution, so the natural distribution, towards that uniform distribution. And we did that with rejection sampling to kind of make it match the uniform. And that's what resulted in this. And it's ultimately still heuristic. So I still don't know what the best distribution to train on is. I don't even know if we should use the same distribution throughout all of training. Probably not. So I think that's an open question that needs future work, and I think it interacts pretty strongly with this idea of data augmentation, because we might get distributions that are just very different from our empirical distribution, and we need to create samples there in order to learn there. Okay, there is code for that online, and I'm happy to discuss that separately. Have 15 minutes left. You guys want to discuss these two? I also have a very quick blurb on a current work that is sort of related. I could do that as well.
Hi, can I have just a quick technical question?
Yeah.
So when you recombine some of the examples from buffer, for the reward, you assume you have like a grand truth reward function, or you also consider like cases
That's right.
when you're like reliable somehow?
Yeah, so we are assuming a ground truth reward function. And I actually don't think this is that wild of an assumption, because very often in modern cases, we are kind of inferring the reward of the task, the task that we're trying to solve separately from the underlying modeling. That's happening even with like large language models these days when we're conditioning them towards a task. That's a very separate process from the underlying sort of policy learning of the LLM.
Yeah, sure. Thank you.
I guess I'll just go on a little bit.
Yeah,
things that I've been
yeah.
Yes. So things that I've been thinking about here is how can we think about this even more generally for out of distribution generalization. And the key pattern that we saw in Coda was that if we can decompose the data and do in distribution reasoning on the individual parts, then we could maybe recombine them in order to form something that is out of distribution with respect to the original. And so the idea is that we think that there's some like general aggregation mechanism that is going to generalize out of distribution. So here, our claim was that our causal understanding of the world is going to generalize well to places that we haven't seen before. And I think this is fairly accurate for the way that humans reason about things. And I guess like kind of the example here is Newton's laws, where we're able to make predictions about a lot of things, even things in space, just by applying these laws that we learned on Earth and then asserting that they're going to apply everywhere. And then we notice, when Einstein comes along, that actually Newton's laws don't apply everywhere. And so our predictions are invalidated. And we get this kind of sort of local causal modeling framework where if we're at, low speeds, Newton's laws apply. If we're at very high speeds, then they no longer apply. And so we need a different causal model of the world there. But generally speaking, we think that these laws, because they apply in so many different tasks here on Earth, they're fairly generalizable and they're going to generalize to new tasks. So, I mean, I don't know, it's more of just another example of this working. I would say this is a much more basic example because we're composing things across time, and that's something that's been done in reinforcement learning since forever. But what we did in this project is we looked at one of the biggest weaknesses of RVS. So RVS is RL via supervised learning, and these are these sort of sequence modeling papers that turn reinforcement learning into a sequence prediction problem by essentially, we're taking the trajectory, we're going to find a state action, and we're going to get the return of the trajectory, so the empirical return that we see, and we're going to associate those into a return conditioned policy. So we're learning this, what would the action be in the empirical data set given that a return G was earned? And then to obtain like our actual greedy or good policy, we're just going to condition this probabilistic model that we learned on a high return. And that's the basic idea behind these RVS methods. But the thing you'll notice, the first thing that I noticed is that this is extremely data inefficient. It'll work when our data set is huge, but well, put an asterisk beside that for a sec. But we're not using the time structure of like the Markov property at all, conditional independence here. And because of that, these methods actually struggle a lot with problems that even need temporal compositionality. So there are, and we show in the paper, problems that an RVS method can just never find the optimal policy for, no matter how much data it has, because the data is coming from an empirical policy that just doesn't have coverage of things that you need in order to learn the optimal policy. But in those environments, say Q-learning, which uses dynamic programming, so it takes advantage of temporal compositionality, can learn the optimal policy. So here's an illustrative example. This is a 6-state MDP, and our offline data set consists of 3 types of trajectories. It's a deterministic MDP. So we have our first, and apologize, I'll just go to the end here. We have our first trajectory here that has a return of 15, so that's this trajectory. We have our second blue trajectory, which has a return of 12, and that's this trajectory. And we have our final third trajectory here, which also has a return of 12. So in distribution, we see returns of 12 and 15. But what we actually would like to learn is this trajectory here, which has a return of 20. And I mean, everyone sees where this is going. The idea is to just stitch the returns together. And effectively, by stitching the 2 trajectories together, we're able to learn that. We could do it in the data itself if we had a tabular state space, but actually there's an easier way to just do the implicit stitching by adding together the rewards using the sort of n-step TD approach. I don't know if I have a slide for that, but essentially we just take the return of the first one and of the first part, and we add it to the return of a second part. And this is sort of the same thing that we saw in Coda, where we have 2 subcomponents here, and we're combining them using this n-step TD relation to create a new data point. And our agent is now going to train instead on a data set of SA, and then augmented returns that represent implicitly stitched trajectories. And this turns out to give the RVS methods ability to bootstrap. So this is one of the D4RL environments that bootstrapping really helps with. So this is an ant maze, and the empirical trajectories, they consist of a lot of things like the ant just not going to the goal. And so in order to stitch together, in order to find the optimal trajectory in this environment, you really do need to say, like, let's say this is like 3 things. You need to stitch together 3 different trajectories. So in the first plot here, the red areas are just a value function of 0. The agent doesn't know how to get to the end. And you can see that there's only a few states from the bottom left where the agent knows how to get to the top right, which is the goal of the maze. But if we do even a single step of this supervised RL with bootstrapping, where we run the algorithm on the previous slide, which is basically train a value function on the current offline data, and then use that value function to augment the data, we're able to get full coverage of the maze. And because this does use a value function in a sense, you can think of it as sort of an interpolation between RVS, no bootstrapping, and then there's like a finite amount of bootstrapping, and then Q-learning over here. So our method is superb, and it can kind of interpolate between RVS and Q-learning. And why would you want to do that? Well, RVS turns out to be pretty stable. It's supervised learning. We know how to do it. It's been shown to be pretty good across a range of hyperparameters. On the other end of the spectrum, Q-learning can do the implicit stitching. It can generalize really well out of distribution when it actually is trained well and doesn't diverge. So there's a lot of training instability with Q-learning because of, say, the deadly triad. In terms of results, we can see here that the baseline RVS that we were trying to train on these like medium and large ant mazes gets pretty much 0 results. But if we do even just a single step of bootstrapping, it starts to do really well, and it gets state-of-the-art performance on some of these mazes. And it gets decent performance across the rest of the D4RL suite too. Like, it's still not as good as CQL. I don't know if anyone's beaten CQL really on some of these tasks yet, but it's pretty good. It does better than the baseline RVS method. So that's that was the idea behind Superb, and I think it fits in the same sort of realm as the counterfactual data augmentation because of this pattern that I described here. Yeah, that's kind of what I had.
Great. Thanks for the talk. It's great. Yeah. Any questions from our audience?
Yeah, I have a quick question. Yeah, thanks for the great talk, Silviu. I was wondering, to your point about learning these mechanisms or learning the factorization, have you seen works like the recurrent independent mechanisms? And I think there's also compositional energy-based models are sort of interesting in this direction. I'm not aware of like the more recent developments in this area, but what do you think is fruitful there in your view?
Yeah, so lost my video. I don't just here. I think so. So in our paper, I guess we contrast between 2 styles of using this kind of factorization. One of them is to build the factorization into the model, which is kind of like what RIM does. That's also what like the slot attention does. And that's kind of what we do in our process for learning the causal model itself. And then the other way is to do data augmentation like we did. And so the question is, how might we think about these 2 different ways of approaching it? I do like building it into the model. In some sense, that's like the way that humans think about these things. It really is like our causal understanding of the world is built into our world model. But I think we give up a lot of control that we might have with a data augmentation approach when we build it into the model itself. So, and what I mean by that is that when we augment the data, we're kind of able to change two things. One is that once we create the augmented data set, it could be used for any agent. So it doesn't need to be an agent that has this thing built into its model. It can be whatever algorithm works really well already. So one thing that we struggled when trying to build it into our model is that our model might have been kind of poor at actually predicting the dynamics, but it was decent at recovering the causal model. Why that might be the case, I'm not too sure. I feel like they should be good at both at the same time, but that could be the case. And the other one is that with data augmentation, you can control the distribution of the data. And that might like allow you to reweight it.
I guess the observation there is that maybe there's some tricks that would work well for getting better factorizations that are mutually exclusive with getting good model productivity, and then you might want to have two separate models. Kind of help each other in that way. Yeah, have you looked at extending this to settings where you don't have this state space, or have you done sort of exploration, don't have the factorization in state space, I mean?
Yeah, we've thought about it. I've been thinking about like actually starting to work on this for a while, but it just hasn't really come to a start yet.
Yeah. One impressive thing I've seen recently is I mean, we've all seen this, the generative modeling has really taken off, especially with conditioned on text, image, text to image models. And there you have this compositional power that is actually very insane, just based on human language. And human language has a lot of the compositional factorization of the real world built into it, so it can pre-leverage that. Do you what are your thoughts on that area? It's like language has this nice design.
Yeah, I'm very impressed by like DALL-E and stuff. And I've been thinking about two things related to it. One was whether we could take language and extract causal knowledge from it. So that would be a pretty cool thing to do. And another was whether, given some causal knowledge, maybe extracted from the model itself, I don't know, but we could use that to kind of predict where these models might do well and where they might do poorly. So what's an example of this? Well, in the large language models, for example, there are some cases where you can give them a new shot and zero task, it'll do it pretty well. Zero shot, sorry. You can give it a new task and zero shot, it'll do pretty well. On the other hand, there are certain places where it really, really needs the few shots examples in order to start doing well. And the question is why? And I'm thinking that one of the times that it can do the zero shot really well is because it's already in distribution with respect to whatever components are within that zero shot task. Like it's already seen each one of them used. And even if we have swapped one out for another, like the interchangeability is really easy for it to do. On the other hand, the few shot, I think why the few shot works because the actual pattern of the few shot reasoning, it's seen a lot of that. And so that part becomes in distribution. And so there you get both the aggregation mechanism and the parts that are all in distribution for it to use. But it's pretty separate from RL still. I don't really know how to bridge the gap there too well.
If you wanted to like directly force the mapping there, I think maybe the connection could be that it has a couple default independent causal mechanisms. And when it gets a text prompt input, it'll be like, okay, these causal mechanisms are maybe important. And we'll try to use those, the default ones, to try and answer the prompt, but they could fail. But if it had a contextual input based on learning so much on the internet, it might be able to look at the context from above and then figure out, based on the context and the answer to the context, what sort of causal mechanisms are actually important to this task that you're going to prompt it with. So then it takes those and assembles them in like sort of few shot way, and then answers it. That's just a hypothesis, but maybe you could in the model-based learning, think about like looking at the recent history of the trajectories that's seen in a multitask setting, and then it figures out which kinds of causal mechanisms that's looked at before.
I think, I think, what was that? Algorithmic distillation paper kind of did something sort of like that for RL. I don't know if you're familiar, but essentially it's just meta learning, but they trained a transformer that kind of imitates the RL algorithm in context. So if you give it a history of an RL algorithm learning so far, it can continue sort of expanding the learning process. So it distills the, I guess, the Q learning algorithm or whatever. That's pretty cool. And yeah, that generalizes to like different environments too that it wasn't trained on. So yeah, I do wish that there were ways to like think about it and with slightly more of a like interpretable like analysis rather than, oh, it just works well.
Yeah, makes sense.
Or at least explain why it works, like by formalizing like that intuition you just gave. I don't.
Yeah. I mean, there's people working on it in the transformer,
Yeah,
large language model literature, but yeah, maybe we'll find some good insights there.
Cool. Any other questions? Yeah, if no other questions, and we are already over time. So probably we can end here. Thanks a lot, Silviu. Thanks for a great talk. And yeah, we can stop recording.
Thanks for having me.